Hey everybody, it's Chili here. Welcome back to 3D Fundamentals Tutorial 7, and today we're talking about texture mapping. So what's the deal with textures anyway? Why are they a thing? Well, the goal of 3D graphics is to reproduce real-life imagery with as much fidelity as possible. There are other goals, but that's the main one, right? And what textures do is they help us realize better fidelity with less resources. So take a look at a scene like this. You got a living room, you got a carpet here. Now, how do you render this carpet? How do you render? Like, we can look at this, we can see that that's a carpet, but how do you know and how do you render it? If you look at a carpet up really close, it's made up of a bunch of bundles of fibers and shit, and we could model it. We could model every individual fiber using, like billions or trillions of triangles. And if you had infinite resources, you could, render all those triangles at a really high resolution, and you would, get something like this. Unfortunately, we don't have unlimited resources. So what we do instead is we take a picture of a carpet, and then what we do is we just paint this picture on top of very simple geometry. So you could represent this floor with, a single quad, two triangles, and then you could just paint this image onto those triangles repeatedly, and then after you light it and everything, you would get image that looks like this. So, and you would not require billions of triangles. Two triangles would do the job for you. And that's the basic idea of textures, right? You're faking the detail by just painting over colors instead of having a bunch of different colored triangles and geometry. You can have some flat geometry, but then you put a picture on that geometry. And that picture could represent carpet or skin or grass or gravel or whatever, wood texture, tiles. And that's how you did it in the old days. That's how you did it. These days, we've got so much goddamn texture memory that what we can do is we can just do a one-to-one painting of all the triangles and then map the texture onto those triangles. So, you couldn't do this back in the day, but now you can, and it looks fucking creepy. It puts the lotion on its skin, etc. Now, without textures, shit looks fucking boring. So we want textures. So the question is now, how do we paint our texture images onto our geometry, onto our triangles? Well, first let me tell you how you don't do it. So when I first introduce rotation and scaling to people, a lot of them, the first thing they try to do, and I've done this myself when I was learning, is they say, okay, I know how to rotate and scale points, so I'm gonna have some source image, some sprite, and I'm gonna scale and rotate the points from that sprite onto the screen, and then I'll get a rotated scaled drawing of a sprite. And that seems like it would work. But when you actually do it, what you realize is that you've only got a finite number of pixels, right? So when you take your source pixels and you, for example, try to scale them up, you're going to be trying to cover a larger area with the same number of pixels. You're going to get holes in your fucking image. It's going to look like garbo, right? Well, let's say you got some geometry, a simple triangle, and you've also got a texture, which is an image that you want to paint onto that geometry. We got a nice little cactus here. And so what do? Well, it starts off the same. You're going to draw your triangle much like you would draw it if you were just doing a single solid color. Only instead of, filling all the pixels with a single color, you are going to, for each pixel in the image here, you're going to look at its center here. You're going to see where is that in relation to the three vertices of the triangle. And you're going to reverse look up into the texture at that point to figure out what color you should use to fill this pixel with. And the way we do this is pretty simple. First of all, we create a mapping of our vertices of our geometry to points in our texture. So now our vertices are not only containing X, Y, Z coordinates, they're also containing coordinates inside the texture, and we call those coordinates UV coordinates. So each one of these guys now, each one of these vertices in the model is going to have X, Y, Z, and then UV. All right. Now, when you transform these vertices to screen space and you start rasterizing them, you're going to get, the points of the centers of the pixels that you're drawing. And what you can do is you can basically, you can take the UV coordinates and you can interpolate them based on this point in screen space. So here you're going to see you're going to get mostly the UV coordinates of the red, and you're also going to get a little bit of the blue and a little bit of the green. And if you mix them all together, you interpolate them, you'll get this point here. Now you guys know how to interpolate between 2 points, right? Like for example, when we draw this triangle, we've got to split it up into flat bottom and flat top, right? So we split it up, we find the split, and we got to find this vertex point here by interpolating between this and this. So you guys know how to interpolate between 2 vertices. So if you want to interpolate between 3, the process is pretty similar. Let's say you're drawing this scan line here. So you know what your y is going to be. So now you can use that to interpolate between these 2 vertices to get this vertex here, which is going to have interpolated UV. And you can interpolate between these 2 to get this one. So you're going to have now UV interpolated 1 and UV interpolated 2. And then as you draw each of these pixels, you're just going to be interpolating between these 2 guys. So the first pixel is going to be mostly this guy, then a little more of this guy, a little more of this guy, and the end is going to be mostly this guy. And that's the way. So first you interpolate between this vertex and these 2 to get the start and end scanned line coordinates in the texture space. And then you interpolate between these 2 guys. And what that looks like in texture space is you're interpolating between this and this. So you get a start that's maybe here, and you interpolate between this and this, and you get a start that is maybe here. And then as you are drawing these pixels going in this direction, you are going to be looking up in your texture in this direction like this. Now, the last thing I want to talk about before we get into the code is something called pre-stepping. So when you are drawing a pixel, let's say we start at the start. This is going to be the first pixel that we draw, right? And when you're drawing this motherfucker, what you're doing is you always draw based on the centers of pixels. That's how you determine whether a pixel is going to be drawn or not. It's also how you determine where the lookup point in the texture is going to be. So what people often do, the mistake that people do, is they start their rasterizer and they say, okay, so I'm starting at this vertex here. This is going to be my start pixel. So I'm going to start looking up into my texture in here. But that's not correct, because we're not starting drawing the triangle at this point. No, we're starting it drawing from this point. So when we start our texture lookup shit and interpolating, we have got to step into the texture by this amount here. So instead of starting from here, we want to start from, for example, here, a little bit into the texture. So you got to take that into account. You've got a pre-step based on where the center of your start pixels are, where the center of the scan line is, and where the center of the first pixel is in your scan line that you're going to be drawing. So we'll see that in the code in a second. All right, let's take a look at the code. It's the tutorial 7 3D fundamental stuff on the GitHub. I'm going to be looking at a lot of the changes. I might not go over all of them, so make sure you look at this code yourself and you review it. Make sure you understand it. I mean, the best would be if you try to code it up yourself, but hey, not everyone got time for that. But if you're not at least looking at the code, I don't know what to say to you, man. So first things first, we added a new file. Well, we added a new scene, obviously, because, we're going to want to show off some new shit. But we also added a new utility file, text vertex. And the reason for this is because, of course, now our vertices don't just contain positions. They also contain texture coordinates. So we can't just put a vec3 and that's the vertex. We've got to have a more complex vertex type that contains 2 coordinates. One for the position, one for the texture coordinate. And I've also added a little utility function that interpolates between 2 texture vertices. So it interpolates both the position and the texture coordinate. And the way I do this is I've also added to vec2 and vec3, I've added a function to interpolate 2 vectors. Just makes the syntax a little nicer. Indexed triangle list. Now instead of doing vec3, it's going to use templated type. So now we can have any kind of vertex that we want, textured vertex or just a simple vec3 if we wanted. And that is going to be reflected in the cube, for example. Now, well, here in the constructor, we're also putting texture coordinates, and I'll get to that in a second, how we map that. But yeah, now we have to set up the texture coordinates for every vertex. And here now get, let me see here, get lines is basically the same. Get triangles now is going to return index triangle list changed. It's now templated, so it returns the index triangle list of vec3 for just get normal triangles. Get textured triangles is going to return a index triangle list of texture vertices. So that's how that works. Not too complicated. The real magic is going to come in graphics.cpp. Well, first let's take a look at graphics.h. What we added was we added a interface function, draw triangle text, and that guy is going to take, 3 textured vertices, and it's also going to take a surface. That's the actual texture. Now, from this front end function, it's going to be calling, flat top and flat bottom. Same deal, only for texture stuff. And what else? So now, graphics.h, this is where the magic happens, right? Now, what I'm going to do here is instead of comparing to previous, because there is nothing in previous, right? We're just adding new functions. What I'm going to do is I'm going to go to graphics.cpp, if I can freaking find it, and then I'm going to drag a window down here so we can compare top and bottom. So we've got draw triangle, and let's see if we can find draw triangle text. There it is, draw triangle text. So let's compare these two motherfuckers, see how it's different. In fact, the top level function doesn't change, almost changes not at all. Same thing here, we're creating some pointers so that we can reorganize the vertices, we can order them, and we're doing the swapping shit. The only difference is now, for this one, the vertices are just vec2, right? For triangle, it's just vec2. It's actually vec3, but, polymorphism and that shit. So all we do is we go vector y, vector y, and then down here, vector x. But here, because we have multiple coordinates for each vertex, we got to specify which one we want. So we go vector position y, here, vector position x. But other than that, it is all exactly the same. It's all the same shit. You can verify that for yourself. We find the alpha split, that is the same. Here, we are calculating the interpolation with some simple vector math. Here, because we can't use simple vector math, we don't have vectors, we have vertices, we've got to use the interpolate to function. That's why I created it. Make this line a lot simpler. Instead of having to interpolate the texture and then the position separately, we can do it all in one line with the interpolate to function. And then down here, it's again the same deal. So basically, draw the top level interface function almost exactly the same. All right, now let's take a look at the meat here, the flat top and flat bottom rendering functions. To start off, basically the same. Again, because we have position and texture coordinates, we got to specify. But other than that, it's the same thing. We calculate the slope, we calculate the start and the end scan lines. And here is where things get a little different. Init texture coordinate edges. So we are now initializing the texture coordinates that we are going to be interpolating across the triangle when we draw it on the screen. So we have edge left, edge right, and bottom, and those are going to correspond to this vertex, and this vertex. But texture coordinates are in texture space, so we're better off drawing them over here. So we got left, right, and bottom. We initialize those guys to these positions in texture space. Now the next thing we do is we calculate texture coordinate edge unit step. And what that means is, well, if you look at the math here, we're looking at the change in texture coordinate on the left side and the change on the right side for every change, unit change in Y in screen space. So basically what that means is take this vector here in texture space and this vector here in texture space, and divide it by this distance, this y distance here in screen space. And what that will tell us is, that'll tell us, well, basically, you know, for every one step in y, how much are we going to step on the left and how much are we going to step on the right edge of the triangle in texture space. That's what this is telling us. So that's edge step L and edge step R. Now we can use that to do our texture coordinate pre-step. So we take, what is this? We take the y start plus 0.5. That gives us the y coordinate of our starting pixel scan line. We subtract the actual position of the y position of the vertex, and that will give us the difference between the center of our starting pixel and our vertex. And we multiply that by the edge step, so we get our pre-step. So what that is doing, again, in nice pretty pictures for you, is, well, if we're going to be drawing this, the first pixel that we're going to draw, rasterize, is this one here, right? So this is not exactly on the vertex. So we're going to have to step by a little bit here, this y distance. So we multiply that by this edge step here to figure out where on the texture we're going to be for our pre-step. So we pre-step along these left and right lines here. See, we're adding to edge L and edge R. So edge L and edge R were originally at the vertex points, and we're pre-stepping them in a little bit based on the difference between the start scan line Y and the Y of the vertex. Now, in these next values here, we're just initializing some constants that'll be useful for us, and they're mainly used for clamping, to make sure we don't go outside of the bounds of our texture when we're doing our texture lookup. So we just initialize texture width and height by getting the width and the height of the texture surface. And then we initialize the clamping of X as the texture width -1 and the texture height -1, because we don't want to go beyond those texture coordinates. We're going to be reading outside of the memory that we have. And then we start our scanline loop here. Just like in the original one, we loop from Y start to Y end. Here we're also looping from Y start to Y end. But we're not only incrementing Y, we're also incrementing the texture coordinate for the left and the texture coordinate for the right. But we're incrementing it by the step left and step right, because we're stepping by 1 y, and step left and step right is how much the texture coordinate changes for every 1 y step. So by adding this and this to our left and our right, what we're going to be doing, well, basically we're drawing scan lines like this, right? Running from left to right. And so if this is our pre-step for left and our pre-step for right, every y scan line, we're just adding a little bit to the left and the right, and we're marching down like this. So as we draw these scan lines left to right on the screen, we're going to be looking up into the texture along these lines here, between the left and the right start points here. Now again, we calculate the X start, let me think here, start and end points. Yeah, so the X start and the X end, again, based on pixel centers with our fill rules. And we do that here again, no change, and no change with the ceiling bullshit. But here's where the change happens, because now we've got to calculate our texture coordinates. We have to well, first of all, we have to calculate the step moving 1 in the X direction now. For every 1 that we move in the X direction in screen space, for every 1 in this space, how much do we move? Let me just get a different color here. How much do we move in texture space? So we calculate that by basically taking this vector from the left to the right on texture space, and we divide it by this distance here in screen space. And that gives us how much change in texture space we get for every change in screen space in the X. And then we use that to calculate the pre-step. So, I mean, if we're drawing this triangle here, we're drawing this scan line. Let's say we start with this pixel. Then we're going to have to step in by this much, meaning we have to step in by this much. So we calculate the unit step in the scan line, basically this step in texture coordinates, and then we use that to calculate the pre-step into the scan line. Once we've got the pre-step, it's basically the same idea as we had here. We're going to loop in the x, we're going to add x, and we're also going to add the scan step to the texture coordinate. Now we've only got one thing to add right, because in the y we've got the left and the right edge, but now we're just interpolating across the scan line, so there's only one thing to add for every iteration here. And then we do the put pixel, right? Except it's just x and y, except instead of putting in just a fixed color, we are going to look into the texture coordinate. So we call texture, the surface, dot get pixel, and then we look into it. Now this is a little strange. First of all, you might be wondering why we're multiplying the texture coordinate by the width of the texture. And this is an important part of texturing. So I've talked about pixel coordinates in Direct 3D already. So for textures, we usually specify the coordinates in the texture in normalized space, meaning that 1 is going to be the very bottom or the very right of the texture, and 0 is going to be, the top left-hand corner. So 0, 0 is top left, 1, 1 is the bottom right. So 0.5, 0.5 is smack dab in the middle of the texture. And there are reasons for why we do this. You can specify both ways in Direct 3D, but most of the time we use UV coordinates going from 0 to 1. And that's what we're going to be doing in the 3D engine that we're building. So when we actually do the get pixel, we've got to multiply the normalized coordinate by the width of the texture to get the actual pixel coordinate in the surface. So we do that, we get the pixel coordinate. Now we want to make sure that we don't go outside of the texture. So we don't want to go beyond, the last pixel in the texture. So what I'm doing here is I'm going std min, and I'm making it so that it's never greater than text clamp x. So if this value is bigger than x here, it's just going to take x. And it's the same thing for y. And the reason why we do this is because with some floating point error, it sometimes goes outside of 1. To be perfectly complete, I should also have a std max here and make it so that it never goes less than 0. But I found that I don't really need that. It doesn't cause any problems, so I've omitted it here. But in general, this is texture clamping, and it's one way of drawing textures. We'll see another way very soon. But yeah, this is how we draw our shit, and it's basically the same idea for draw flat bottom. There's not much change here. You can examine it yourself if you're interested. And so let's take a look at how that looks on the screen. So if we tab through our scenes here, we get to what I like to call Sauron's butthole. And here it is in all its glory. Beautiful. I mean, it might look a little weird. It might look like his butthole is puckering just a little bit, but just pay that no mind for now. We're just going to pretend like that's not a thing. So yeah, here you got your textured cube. Looks pretty fucking sweet. Now, you might be wondering, why is the top and the bottom all fucked up? Why is my shit all jacked up here? And the reason is because the limitations of how we are representing this cube and how we can map the textures. So let's take a look again at the cube itself. Where is that? All right, well, here is our model of our 3D cube. Now, our cube has 8 vertices, and those vertices are being shared by a bunch of different triangles. So, if we want to put a texture on, let's say, this face here, what we can do is we can map, so this corner here is going to map to this point on the texture, which is going to be, 0, 0. And the same for this one is going to map here, this one's going to map here, and this one is going to map there. And if we do that, then we're going to get our good old texture dude drawn on here. Great. Well, what about this face? Well, what we can do is because these guys share vertices, we can't change this one for this face. So this one has now got to map to here. and this one has got to map to here. We've already set that. So we can't have it going left to right again, but what we can do is we can flip it. So now we can map the right corner to the left of the texture, and this right corner to the left of the texture. And what we'll get is we'll get the eyeball basically reversed. It'll be mirrored in the x-axis. So if you had an arrow pointing to the right, in this one it would now be pointing to the left, but you'd still get your Sauron's butthole. It would still look good, right? And you could do that for these 4 faces here. But the problem is, if you do that, you've now set the texture coordinates for all the vertices. They're all set. What happens for the top and the bottom? Well, it's going to look like this, right? You're going to have your goddamn red and blue, and that's it. So you're only going to have your vertices for the top are all going to map to either this one or this one. That is not going to give you the full texture. That's only going to give you this top line. And that is what you are basically seeing in the image. You're just seeing the pixels of the top line interpolating across here, and it's a diagonal pattern because this one is the same as this one, and this one maps to the same point as this one. So you get this kind of diagonal striation pattern, but you're not going to get the texture image because our hands are tied, right? All of these vertices are shared and they're fixed. So once you set the images for the sides, you got no choice. You're stuck with this bullshit for the top and the bottom. It's no good, and we're going to solve that problem a little later. But first off, let's do a little bit of improvement on our texturing code. So one thing that we can notice with our triangle texturing code now is, let me see here. Let me just see. We got draw flat top triangle. All right, so what we're doing is basically in our texture drawing code here as we have it so far. We're taking our normal triangle drawing code where we loop through the x's and the y's, and then we're interpolating texture coordinates during that process. But when you are drawing a triangle, you could also think of it as interpolating. Let me just get some shit up here. You could also think of it as interpolating not only the texture coordinates, but also the coordinates in space themselves are kind of being interpolated. We're treating it as a loop, and we're calculating the slopes and everything. But you could also think of it as interpolating between these coordinates in space. And if we do it like that, we could actually unify our system. So instead of having our loops and calculating our slopes and our start and our end points, we could just have it as interpolating x and y and interpolating u and v, unified all together, make the system a little sexier. And that's what I do here. So here, instead of calculating the slopes for the coordinates in screen space, what I'm doing is I'm calculating the change in all of the vertex coordinates for every change in y. So not only the change in u and v, but also the change in x and the change in y for every change in y, which should be 1, right? That should just be the same. And so now we are interpolating the whole vertex, not just the texture coordinate. By the way, I forgot to mention it, but in order to enable us to perform all these operations on whole texture vertices, what I ended up doing is I ended up adding a bunch of operators to the texture vertex class. So now we can treat it as a mathematical type and do all sorts of, interpolation type bullshits on it, all sorts of operations on the entire vertex that work on the texture coordinate and on the space coordinate simultaneously. And you see here that actually removes a bunch of bullshit code and makes our code shorter. So we create edge interpolants, and that corresponds to here creating the texture coordinate edges. And then we calculate the start and the end scan lines. That's mostly the same. And then we do the interpolant pre-step. So now we're not only pre-stepping the u and v, we're also pre-stepping the x. And then this is the same. And then here, we're not calculating the start and the end x based on the slope. The start and the end x is just going to be the interpolant position x minus 5 ceiling. So we don't have to use the slope to calculate the start and the end. That is included in the interpolant. And then we just do the scanline stuff here. What is this? Oh, here we're actually only, for the scanline, we're only interpolating the texture coordinate. We're not interpolating the x and the y because that's all now going to be fixed by the loops. There's no sense in interpolating that stuff. So here we switch to just interpolating the texture coordinate. And then here's the pre-stepping of the texture coordinate. So this is the interpolant for the texture coordinate going across the scan line. And we take the texture coordinate of the left-hand side, edge 0 is the left-hand side, and we pre-step into that, and then that is what is going to get added to in the loop. So we unify the interpolation so that we're now interpolating both the screen coordinates and the texture coordinates. And we're no longer using slope calculations for every scan line. Now we can do that for the flat bottom again, and then what we can notice is the flat top and the flat bottom algorithms, they're almost exactly the same. They only have a little bit of difference between them. So what I did is I factored out all of the parts that were the same, and I put that in its own function. So now what we have is draw flat triangle texture, and then we have draw flat top and draw flat bottom. So draw flat top and bottom will do the parts that are different, and then they will both call draw flat triangle, which does the common parts. So flat triangle takes a few more parameters. It takes the delta for the left hand side, that's delta v0, delta vertex 0, the delta for the right hand side, and it also takes the interpolator for the right hand side, because that differs between these two cases, so it has to be decided in these functions here. So now we see all that draw flat top triangle text does is it calculates the d vertex over dy, the deltas, and it calculates the right edge interpolant, which is just going to be v1, right? And then it calls draw flat triangle texture. Now, draw flat bottom, again, it calculates the deltas, and it calculates the right edge, which is v0. Notice that that's different, and this one is v1, and so that is why we have to separate that out and pass that into draw flat triangle. But once we have those parts calculated out, draw flat triangle is going to do the same shit that it always did before, and except now we have it in a single function instead of two separate functions that are almost identical. And that's better for code maintenance, and it's just good shit. So now that we have our triangle drawing routines, our texturing routines all refactored and sexified, we can add a little bit more features to the system. So up until this point, we've just been doing what is called clamped texture rendering, and we haven't been repeating textures at all. It's just been this deal here. Oh, by the way, in this next set of changes, I added a thing where it outputs the name of the current scene to the window here, the debug window. So right now we're textured cube, butthole of Sauron, clamped, dimensions 1. So it's just 1 by 1 fitting the cube. Now if I go to the next one, here we've got clamped, but I've got 2. So the texture coordinate for the left here is now 0. This is going to be 0, 0, and this one's going to be 2, 0. So what happens is it reaches 1, and then when it goes beyond 1, it just gets clamped to that, and it just repeats. It just smears out those the last pixel, and then you get this kind of pattern here. So that's what clamped looks like when your texture coordinate goes beyond the texture. It just clamps it like this. Now, what happens if instead of clamping, I wrap? And I'm not talking about Eminem's magnum opus rap god here. I'm talking about, well, if the texture coordinate exceeds 1, it will wrap around back to 0, and thus it will repeat, and we will get something like this. This is what texture wrapping looks like. And something like this can be used to, for example, the example I gave at the beginning of the video, to texture a floor with some carpet, you can have a repeating texture. It looks kind of dumb with, the butthole of Sauron. Here's it with texture coordinate 6. So now it's going from 0 to 6, and we're getting 6 repetitions in the X and the Y. But yeah. So in order to do the texture wrapping, I add a new set of functions. So we have draw triangle text. Now we have draw triangle text wrap. And again, we've got, flat top, flat bottom, and just normal one. These are the implementation functions. And the way that they look is they're almost exactly the same, except for one little difference. And that little difference is, instead of doing std min, we do std f mod, modulus. So modulus will mean that, if we reach, for example, the value of 1, it will wrap back down to 0. And likewise, if we go into like -3, it will wrap around to 0.7. But yeah, the other stuff is exactly the same as before, and this is what gives us texture wrapping. Now let's go back and address that problem of texture mapping the top and the bottom. So like I said, because all of these faces share so many vertices, we get stuck not being able to texture every face. If we map this one to 0, 0, 0, 1, 0, 1, 1, 0, 1 like this, it's going to give us problems. Now what we can do is we can actually unfold the geometry a little bit and basically break the welds between the sharing of vertices between some of this geometry. So now, like here we have the texture, here's 0, 1, and I'm putting, 0 here, 1 here. So Y is going to the right, whereas Y is going up here. You gotta tilt your head a little bit. But we can unfold this cube and it will make a shape like this. And if we do this, now the textures are independent enough that we can texture the top and the bottom. And there are a number of ways we can do that. We can make it so that they share vertices and are mirrored. So for example, if this arrow was pointing this way here, it would point this way here, and it would point this way here and this way here. Using our texture clamping system, we could do this. Now another way you could do it is with texture wrapping. So if we said that this was 0, 0 here, and this is going in the Y direction, this would be 0, 1, 2, 3, 4. So this would be 0, 4. And here we could say this was 1, 1. And so that would mean that here this would be 2, 1. And likewise, this one would be -1, 1. You get the idea. So, and in this case, they wouldn't be, mirrored. They would all be facing the same direction, which is nice. So you could solve that problem with texture wrapping or texture clamping, but you have to you have to make some of these vertices independent. You can't have perfect sharing of vertices. And this is going to increase the number of vertices in your model. Here we had 8. In this one, we have how many? Here we have 14. So, and if we were to split it up so that every face was an independent square, we would have 6 times 4, 24 vertices. So the more independent you make your vertices, the more work you're going to have to do to render them. But you're also going to have more flexibility when it comes to texturing them. So here's the original texturing scheme, 0, 1, 1, 1, 0, 0, 1, 0 for the 8 vertices. Now when we unfold the cube and do the same thing, it's the same idea, 1, 0, 0, 0, etc. But now we're doing it for 14 vertices. We've got more vertices to work with. And if we unfold the cube, but we do wrapping, now we can see a little difference here. Now we got coordinates like 1, 3, 1, 4, etc., -1, 1. So again, 14 vertices, but now we're wrapping, and that will give the geometry, there'll be no mirroring anymore. They'll all have the same orientation. And if we tab through, we can see all the different stuff we got here. Weird X shape textured, that's wrapping. Here is folded texture clamped. And you can see now we've got texturing on all the surfaces. Folded texture wrapped. And again, it's texture on all surfaces. If you look really closely, you can probably tell that one is mirrored and the other is not mirrored, but we're gonna go into that level of anal retentiveness. And what else do we got here? And then we go back to the start. All right, so that's all I did for that one. Now we can take things a step further, because now that we've unwrapped the texture, instead of repeating a pattern on it, we can create a skin for the geometry. Now that we've unwrapped the geometry, we can create a skin for that geometry that is the same shape as the unwrapped geometry. And then we would just map it so that the points on the triangles map to points on this texture. And when I did this code for skinning the cube, I was super lazy. So what I did was I copy and pasted the code for the unfolded wrapped texture. You can see here it's got the coordinates going to 0 to 4, -1 to +1. I took these ones and then I just divided them by the dimensions of the texture. So I took the U, I add 1 to shift it over because we had -1s, and then I divide by 3, and then I take the V and I divide by 4, and that converts it to textures in this space here. And it saved me some work, which I like. So now we can provide a texture that uniquely skins all of the faces of the triangle, and that is going to look like, let me just get to it here, wrapped cube, here we go. We've got the dice. Here's dice, what's this? And we've also got a weird office scene. So yeah, now we can skin our shit. And it's basically the same idea, just a little bit different. No repetition this time. Everything is uniquely identified in the texture. Now, remember I said I was going to tell you the advantage of using normalized coordinates for your textures. So let's say you've got two textures. It's the same image, but one is going to be a much smaller resolution. So high resolution image, low resolution image. This one's maybe 400 by 400, and this one is maybe 100 by 100. Now, if you specify your texture coordinates as texels, so this would be 0, 0, this one would be, like 400 or 399, 0, etc. This coordinate, these mapping would work for this texture, but if you tried to switch to this texture, it would obviously be bad. It would be going way outside the texture. But if you map normalized to, 0, 0, 1, 0, 1, 1, 0, 0, it will work for both of these textures. You can switch between them and you don't have to change the texture coordinates. So you can dynamically switch between the different levels of detail, different texture qualities, and you don't have to change any of your texture coordinates because 1 always means, the edge, and 0 means the other edge. And it doesn't matter the size of your texture. So for example, take a look at this one. We're texturing it with a high quality texture, but if I hit tab, now we're in the low quality one, hit shift tab, back to the high quality, and it's the exact same texture coordinates here. I'm just using the same texture with different resolutions. One more thing, because I didn't give a really good example, but here I've got the repeating texture. It looks kind of dumb, but if you replace it with a seamless texture like a wood paneling, you can see it looks pretty cool actually. It's not bad. We'll ignore the top and the bottom part, but yeah, so this is what that texturing looks like. Wrapped texturing with a proper seamless repeating texture. And that's it. That's all the code that I did for this tutorial, all covered. That, my friends, is texturing. Now, there are other things that we could talk about. So if we take a texture like this and we zoom in on it really far, we see that it gets very pixelated. And usually you don't want that pixelated look. So what we do is we do something called bilinear filtering. Normally, we just take basically the closest pixel and we use that when we're filling the screen. But with bilinear filtering what we do is we actually we do a weighted average between the 4 nearest pixels. So if the sampling point here is C, we are going to average between, C01, C11, C00, and C10 to get A and B, and then we're going to average between A and B to get C. That's how you calculate bilinear filtering. That's a setting that you have when you're rendering in Direct3D or OpenGL, but we're not going to do that shit. Like I said in the beginning of this series, we're not worrying about the aesthetic shit. We're getting the basics down. So we're not going to do bilinear filtering. There are other kinds of filtering technologies. Bilinear tends to deal with what happens when you magnify things, what it looks like. There are things like MIP mapping and anisotropic filtering, and these tend to deal with what happens when you shrink shit and what happens when you shrink it at a different ratio in the X and the Y. And obviously, the more of this shit you use, the better your shit is going to look. But I'm not going to deal with those details in this series. I might take a look at it in the actual Hardware 3D series. Basically, the way that MIP mapping works is instead of just storing the texture, you also store versions of the texture that have been sized down. And isotropic also stores versions that have been sized down in only one axis, X or Y. And that gives you, very nice scaling when you scale shit down. For example, here's what happens when you don't have MIP mapping, and here's what happens when you do have MIP mapping. It's a lot smoother, right? When you're scaling shit small. But yeah, that's texture mapping, and it's a very important concept, not only for the texturing, for the mapping colors onto your geometry, but there are other things that you map as well when you're rendering 3D graphics. Like you have normal maps that actually map the surface geometry, the directions in which the surface is facing, basically bumps on the surface. And those are normal maps, and you map them to pixels on the screen the same way that you map texture maps to pixels on the screen. Here's an example of effective use of normal mapping. Here's a model with 6,000 polygons. Here's a model with 6 million. You can see a lot more detail in the wrinkles. And here is the model with, again, 6,000, but it has a normal map. And the normal map creates the wrinkle detail without blowing out your polygon count. So yeah, this idea of mapping and reverse lookup and interpolation, very important, and it comes up all the time. So I encourage you to, download the code that I've made here, look over it yourself, make sure you understand the concepts because they're pretty important. They're kind of a big deal. And as always, if you have questions, ideas, discussion, hit me up on the Discord, hit me up on the forum, and we can talk it out. It'll be fun. But that's it for today. I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more 3D fundamentals.